Well, anyway, I so wish you were here. I so wish that you were here, but fate has dealt us another hand, so we're just going to have to do the best that we can. So this is the first discussion, and everything is very tentative, whether this works or not. This is just something that we'll have to assess, and if this approach doesn't work, we'll just have to try something else. And uh, if there are technical snafus, and if the recording doesn't work out or whatever, please bear with me because this is all uncharted water to me. So I thought maybe we could have we could present some problems. I'm going to write them up here on the whiteboard, present some problems, and talk about some of the reactions. And I'm going to make the recording available and post that somehow on Blackboard or uh, otherwise, so that you can have a recording of our little meeting. Okay, so let's talk about some stuff that we haven't had a chance to talk about yet. Let's talk about some reactions. Oh, yeah, let's talk about some reactions. I guess this is reductive amination. So can you sort of see that? Reductive amination. Okay, the overall reaction is you're looking for a primary amine. And what does primary amine mean? It means NH2, but nitrogen is bonded to a bunch of, nitrogen has 3 bonds, so that this nitrogen atom will always be bonded to something else. I'm just calling that Z. And then there is an aldehyde or a ketone, aldehyde or ketone. The conditions for this reaction are normally acidic. Oh, there's an annoying shadow there. Normally acidic. And what happens here is that the carbon-oxygen double bond is replaced by a carbon-nitrogen double bond. The carbonyl oxygen is gone. It comes out in a molecule of water, and the 2 hydrogens on the nitrogen atom are also gone. They come out in that molecule of water. The carbon-oxygen double bond is replaced by a carbon-nitrogen double bond. That's the imine, but the imine is not the final product because this reaction is conducted in the presence of a reducing agent, and you have several reducing agents available. You could use sodium borohydride, or you could use sodium cyanoborohydride. Oh, none of these things work. You could use sodium cyanoborohydride, or you could use hydrogen and a nickel catalyst. You could also use platinum and so on, platinum or palladium. And anyway, the product here is going to be the reduction of the carbon-nitrogen double bond to a carbon-nitrogen single bond. So remember in Orgo 1, the carbon-carbon double bond was reduced by hydrogen to a carbon-carbon single bond, and hydrogen was added across where the double bond used to be. Well, it's the same thing that is happening here, except that now it's a carbon-nitrogen bond. Okay, so that's That's reductive amination. Okay, so let's try a product prediction problem. All right, so let's say benzylamine plus cyclohexanone, let's have sodium borohydride present, and let's say this is happening at pH 6. So what that pH 6 is telling you is that it's acidic conditions. So that's just the same as writing H plus over the answer. Okay, so I'll give you some time. Let's draw the structure of the product. And then we will divulge the answer. So maybe right now you can, I hope you can see that. I hope everything is hunky-dory for you. And you could try the, draw the structure of the product. Give you a couple of minutes for that. All right, so the carbon-oxygen double bond is replaced by a carbon-nitrogen double bond. The two H's on the nitrogen are gone. They come out in a molecule of water, but that third substituent, which would have been this benzyl group, remains. And so we get that as we get this as the reductive amination product, right? Where of course there's a hydrogen here, but I'm not writing it. It went through the imine, but then the imine was reduced. So did we get that? Let's try another one. What about acetophenone plus isopropyl amine? Maybe this time we would use sodium cyanoborohydride and acidic conditions. And so what would the structure of the product here be? So you try it out on your own, and then we will divulge the answer. So how are we coming along there? Did you get it? Okay, so the carbon nitrogen double bond replaces the carbon oxygen double bond momentarily anyway, and then that carbon nitrogen double bond is reduced to a carbon nitrogen single bond, and hydrogen has added across where that double bond used to be, right? So that would be the structure of the product there. Okay, so that's reductive amination. Let's try reductive amination in a synthesis problem. So what about the following synthesis? Let's try this. How would we synthesize this molecule from bromobenzene plus this epoxide plus methylamine? Okay, so let's try to develop a retrosynthesis for that. Okay, so the compound that we're trying to make here is crystal meth, right? This guy here, crystal meth. So don't say you never learned anything practical in Orgo, right? So let's see how we could go into full scale manufacture of crystal meth, like maybe in somebody's bathroom or something like that. Okay, so as usual, what we always want to do is we want to approach these problems retrosynthetically. Okay, and so we see this is our target, and as always, we ask ourselves, we're dialoguing with the target, and we see that there's a functional group that we know how to introduce. And in this case, the functional group that we know how to introduce is this carbon nitrogen uh, single bond. And so if we wanted to do this retrosynthetically, we know that the carbon nitrogen single bond is the result of the reduction using, we could use sodium borohydride or sodium cyanoborohydride. It's the reduction of this imine to this amine, where the carbon nitrogen double bond is reduced to a carbon nitrogen single bond and hydrogen is added across where the double bond used to be. Okay, and this guy has a functional group that we know how to put in as well, and that is that carbon nitrogen double bond. And so that is the reaction of the primary amine with an aldehyde or a ketone. And what we usually go for in this reaction is acidic conditions. So I've written it as two different steps, but it can actually be all accomplished in one step, where you mix this plus this plus this, mix all these three together, and come up with a target molecule. Okay, so now this methylamine, that's the one of our starting materials, so we've taken care of that. Okay, and so now this is our new target here. We want to develop a synthesis for this. Okay, and it's a ketone. How do you make a ketone? Do you remember? How do you put in that carbon oxygen double bond? Give you some time to think about it. You know a couple of, I think 3 reactions that will do that. So it could be Jones, or it could be PCC, or SWERN, or DMP, all of the various ways of oxidizing an alcohol to a carbonyl compound. And so you could oxidize, I'm going to use PCC, but you could use Jones or DMP or a bunch of other stuff. Okay, and so now this is our new target, which is an alcohol, and we have bazillions of ways of making an alcohol, but what I see here from my starting materials is this carbon put a dot on him, this carbon put a dot on him, this carbon put a dot on him. It's pretty clearly these 3 right here. And it looks like the phenyl ring has attacked a carbon atom, the less hindered side of this epoxide, opening it up, and the molecule we're trying to make here, this thing, is an alcohol where the carbon next to the alcoholic carbon has the remnant, what is left of the nucleophile. And if you'll remember, that is how we the result of opening an epoxide. So we need a nucleophile that attacks the basic. We need a basic nucleophile because we want the less substituted side of the epoxide attack. So the nucleophile that would bring, the basic nucleophile that would bring that about would be the Grignard reagent, phenyl magnesium bromide reacting with this epoxide. More hindered side, less hindered side, basic nucleophile opening up the less hindered side. and then work up with aqueous acid. So we've used him in our synthesis of crystal meth. All right, now we need to remember how to make a Grignard reagent. And if you remember the how to make a Grignard reagent, yes, are the memory banks working here? The dials are turning. Yep, you add magnesium to the corresponding organic halide. So you would need this you'd need this phenyl bromide or bromobenzene. And so that's the last of our starting materials here. So this would be a very nice laboratory synthesis of crystal meth. This is not how the experts make it, right? This is something that only people with access to fancy laboratory equipment could carry out. It also employs this methylamine and this propylene oxide, which are very heavily watched by the federal government DEA, Drug Enforcement Agency, because so much of this stuff is diverted toward illicit drug manufacture. In other words, this kind of synthesis. Okay, so I want to return to how the pros make crystal meth because it's actually quite relevant. But before we do that, let's talk about another reaction of aldehydes and ketones with amines.